Okay, I'm going to move to our next speaker, which I think Nina's talk feeds beautifully into Michael Waring's talk. And so Michael Waring is the department head and professor in the Department of Civil, Architectural, and Environmental Engineering at Drexel University College of Engineering. And he's going to tell us, we've been hearing a little bit about it, but he's going to give us more detail on secondary aerosol formation of fine particulate matter in the indoor environment. Michael?
Yeah, sure. Thanks, everyone. So my name is Michael Waring, like was introduced, and I'm at Drexel. So thank you for attending my talk today entitled Secondary Organic Aerosol Formation of Fine PM in the Indoor Environment. Sorry, I'm just going to advance. Okay, so this is the outline of my talk. First, I'm going to give an overview of SOA formation indoors and give some quick background so we all start with the same understanding. Second, I'll talk about SOA modeling techniques with the focus on the type my group has done to contextualize results and research needs in the third section. And then third, I want to discuss various factors that influence indoor SOA emission strengths, many of which I think need more research. So, right, organic aerosol, just to start out, is composed of hundreds or thousands of different types of molecules existing in a state of dynamic equilibrium between gas and particle phases. So, using mass spectra, this organic aerosol, or what I'll call OA throughout the talk, can be categorized into different factors corresponding to their emission type and character, including source types such as HOA, BBOA, COA, or OOA. Also, we distinguish primary OA, which is that material which partitions between phases quickly after a primary emission, from secondary OA, which is that OA that is changed in mass, number, or composition over time due to chemical reactions. So most indoor formed SOA we think is probably due to ozone or OH reactions with terpenes, which are compounds that are present indoors that have at least one carbon-carbon double bond and are generally at higher concentrations indoors than outdoors, since they are emitted by building and consumer products. Earlier, Delphine showed SOA originating from chlorine chemistry, but I won't be talking about that today. So just to give a little background on how SOA forms, so the mechanism is complex and multifaceted. So looking at ozone alkene reactions, for instance, so when ozone reacts with a double bond in an alkene, like a terpene, a primary ozonide is formed that then splits to form a carbonyl and an excited Kriege intermediate, and then that SCI can be stabilized or can rearrange to yield OH and an alkyl radical indoors. So these ozone alkene reactions, by the way, are also one of the most important sources of OH in our buildings. So after that, these alkyl radicals produced by ozone alkene reactions go on to do other sorts of chemistry. So these are also generated when radicals like OH, for instance, abstract the hydrogen from a VOC. So what happens is the alkyl radical will go on and react with oxygen to make proxy radicals, which can then react with other compounds to form different classes of products such as carbonyls and alcohols, carboxylic acids and peroxides, organic nitrates, etc. And it's these larger and low volatility compounds in this group that partition to form SOA. So historically, most studies on indoor SOA formation have been conducted in chambers or test rooms with intentional releases of reactants. There are a few here. Most of these earlier studies measured SOA formation using particle counters like scanning mobility particle sizers. These are very good for controlled experiments with strong SOA signals. Also lately, aerosol mass spectrometers are a major improvement in measurement capability, and they give compositional information on aerosols, so they're much better at showing chemical trends over time. Okay, and so additionally, besides this dedicated chamber and certain sort of small field work, there's been a lot of indoor SOA insights that have been gleaned from using indoor SOA formation models. And that's the bulk of how my group has advanced this. And so I'll be talking about that next. So before we get on to the models, I just want to sort of ground us in what SOA formation looks like. So here's an example of SOA formation in an experiment run to steady state with time on the x-axis, particle diameter on the left axis on the bottom, and then particle intensity as a color bar. And so these are results for an air freshener operated in a chamber at 3 air changes per hour, into which ozone was supplied at 63 ppb, starting at this red line at time 0. So you can see that almost immediately a strong burst of nucleation commenced in which new small SOA particles were formed. These then started growing into larger particles by gas to particle partitioning mechanisms, and then the size distribution started stabilizing over time. So after a steady formation event occurred, which was balanced by chamber losses, this continued until the end of the experiment, until the ozone supply was turned off, and then everything started to decrease. So as shown in this quick example, SOA can be formed both by nucleation mechanisms and by gas to particle partitioning mechanisms. So having generally introduced SOA, this next section overviews SOA modeling, mostly as my own group has performed, so as to motivate the third section of the talk on research needs. So there are two main ways indoor SOA is modeled in the literature. So the first I'm not going to talk about. This is mostly from Nick Carslaw's group. So this is what could be termed an explicit product model, where products are explicitly tracked and then they're assigned partitioning equations, and then they can partition into some existing generic organic aerosol. So the second is what I do more of, and this is called a lumped product model. So this uses a simplified mechanism to account for first generation reaction products, but then explicitly following that, reaction products are treated as lumped generic organic mass that is lumped into a certain number of volatility bins, and then partitioning to the particle phase can be computed once you know those volatility bin distributions. So this model type, has particular strengths relative to the explicit product model. Some are that it can account for any arbitrary type of organic aerosol source from indoors or outdoors. It's not limited to SOA. It also allows easy computation of bulk aerosol properties such as density or hygroscopicity, et cetera. And so my group's model is of this format. It's called images in its current iteration, and this is the indoor model of gases, aerosols, emissions, and surfaces. So I'll talk more about this as we go on. Okay, just to set more groundwork for modeling and SOA formation. So this is a typical chamber study. So let's take a look at how this is working and how we can describe its formation. So let's look at formation in this chamber for ozone plus alpha pinene reactions. So alpha pinene is shown in red on the left. It decreases over time to 0 as it reacts with ozone, while the SOA shown in blue increases over time. The amount of SOA formed can be parameterized with the SOA yield, or the aerosol mass fraction, which is defined as the increase in SOA concentration normalized by the decrease in the reactive organic gas concentration. So that's shown in this equation here. And this metric can also be expressed as the sum of the mass yield of these bend oxidation products organized by volatility according to effective saturation concentration for each bin, which is the volatility representation in the model. Results from chamber experiments can then be recreated using the yield equation shown on the left with fits for alphas shown on the right over these logarithmically set C star bin values as described here. Okay, so these yield results, these started pretty early on in the outdoor and indoor air literature, and so they've been adapted a little bit and put into a more holistic model, which I'll talk about now. So yield results like from this previous slide can just be displayed also as lumped organic matter concentrations due to ozone alpha pinene reactions per C star bin, such as in this framework here. So this is what's known as the one-dimensional volatility basis set. So just like we had ozonalysis products in the previous bin that were understood by their mass formation trends, this is a similar set of alpha pinene ozonalysis products, not discerning whether they're in the gas or the particle phase at this point, with all of this potential organic matter being arranged by bins of volatility, in this case with 4 bins ranging from 1 to 1,000 micrograms per meter cubed in C star. So with this VBS, with this volatility basis set, the aerosol mass fraction in each bin can then be computed with partitioning equations. And so the total OA concentration can be determined. So in this example, the total amount of OM is just at 40 micrograms per cubic meter. But when you compute the partitioning equations, you see that it's about a quarter of that, or 10 micrograms per cubic meter of that total OM that actually partitions to form SOA. Okay, and so again, any type of OA type can be resolved as ON and simulated using the VBS, whether it comes from outdoors or indoors or is primarily emitted or secondarily emitted. So our model goes beyond the 1D VBS. It actually uses the 2-dimensional volatility basis set. So this takes that identical set in the 1D space of OM organized by only C star and also spreads it into a second dimension representing degree of oxygenation, which is measured or quantified in our case by the O to C ratio. Okay, and so please note that the number of bins in this example versus the previous one has increased from 15 bins in the 1D VBS to 165 bins of volatility plus OC in the 2D VBS. And then with all this information about volatility and O to C ratios, we can get additional information into the compositional aspects of the bulk OA that we're modeling. Again, partitioning is still driven only in the C star dimension, and so partitioning equations remain unchanged from the 1D VBS before. So, you know, the 2D VBS, it doesn't just offer more information on bulk aerosol properties, which are driven by composition, including things, again, like aerosol density, aerosol phase state, and hygroscopicity. But the 2D VBS can also account for OM reactions in any part of this space with the hydroxyl radical. And so we can simulate OH aging of this lumped organic matter as well. So first, you know, in the 2D VBS, OM forms by VOC oxidation, and you can see on this slide that it will make a certain amount of products that are situated in this space. And then that OM that's formed initially can react with OH and move around the 2D VBS space. So it can functionalize, meaning it gains functionality, it gains oxygenation, which moves it in the 2D space to an area representing lower volatility and higher O to C compounds. And then once it's sufficiently oxygenated, further reactions with OH can cause the OOA to fragment, and then it can move it to higher volatility regions. And so in this case, if that happens, you get evaporation from the 2D space, and it evaporates from the particle into the gas phase. So, you know, I don't want to get into the math, but the 2D VBS handles these OH reactions using transformation kernels, where each bin has a probability of OM moving from one bin to another after reacting with OH. Okay, last section on the model framework before I discuss some results with it. So here's a schematic overview of our residential model, starting with sources and then losses. So regarding sources, our OM can be sourced from outdoors with air exchange, along with ozone and 66 different VOCs that we're accounting for in the model. The OM can be emitted as primary organic mass indoors, along with emissions of HONO, and again, those 66 VOCs. Secondary chemistry can occur. So secondary OM can be formed via VOC oxidation by ozone or OH. OH can be formed by alkenose analysis or photolysis of HONO. OM can be aged via the 2D VBS aging scheme just shown. And so that's all the secondary chemistry that can occur. Regarding losses, OA and ozone can deposit on surfaces, and then all species can be lost to air exchange. So there's a bunch of differential equations, of course, underlying this model, which are not shown here in the interest of time. Okay, so with the model explained, I'm going to now move on to the third section of the talk, which is using this model to demonstrate common indoor residential concentrations of SOA and future research needs related to emission strengths. So the model has been used to estimate the likely magnitude of SOA formation from VOC reactions with ozone or OH in typical residences in the United States using a Monte Carlo approach with day average parameters. So using data from the RIOPA study and other sources, input log normal probability distributions were determined, parameterized by the geometric mean and geometric standard deviation for things like air exchange rates, deposition rates of ozone and PM, outdoor concentrations of ozone, OA, and inorganic aerosol, indoor emissions of primary OA and IA, outdoor concentrations of 66 VOCs, and their indoor emissions of those same 66 VOCs. So the VOCs modeled, of the 66, there were 6 terpenes that were modeled, plus other alkenes, alkanes, aromatics, et cetera, and all had probability distributions for their concentrations outside and their emissions indoors. So in this Monte Carlo operation, 10,000 unique cases were simulated using those distributions, allowing results to also be generated as probability distributions. So here are some results, right? And so we want to know with this model, what are typical SOA values predicted to be in indoor US residences. So these are those distributions. This is showing box plots over all 10,000 run cases for things like indoor OA by type, indoor OA and inorganic aerosol, and the total indoor PM. And so things to note on this plot include these items. We found that in this modeling study, much indoor PM is often organic aerosol. Primary OA typically dominates indoor OA, for instance, from cooking, as we just saw from Nina. And also SOA is typically the smallest of the OA types indoors, with the median value at 1 microgram per meter cubed. However, the plot clearly does demonstrate that SOA can have very small or large values, and that SOA can dominate the OA PM fraction sometimes, likely when ozone and terpenes are high and air exchange rates are low. So we do see that in our model. So the rest of the presentation highlights some research needs denoted by these R+. So the first research need comes out of the just discussed residential modeling effort. Across all 10,000 simulations, this plot shows the fractional amount of SOA due to the oxidation of each terpene in the model. So the first 6 labels correspond to the model terpenes, and then the reaction rates and the indoor concentrations are also shown. So what this model shows, or this plot shows, is unsurprisingly, most SOA came from D-limonene. Okay, this is typical. We think this drives a lot of indoor chemistry. However, the next most important SOA driver ended up being alpha-terpenine, which I was surprised by. It had a very low indoor concentration, but what it had is a very fast reaction rate, 10 times faster than limonene, even though its indoor concentration was 2 times lower. But it's still, of all of the VOCs examined, ended up being the strongest driver of SOA formation in the model. And so this made us think that this combination for alpha-terpenine of being a fast-reacting terpene but with low concentration demonstrates a concept that should be explored indoors, namely that low concentration, fast-reacting stealth reactants may be present that have large impacts on SOA formation. Another research need involves investigating whether the phase state of organic aerosol has influence on SOA partitioning and whether equilibrium assumptions driving partitioning indoors is truly valid, or whether SOA formation might be kinetically limited instead. So to determine this, we ran our images model again using the housing simulations that I showed before, but this time run in 16 cities over all US climate zones with historical data. So we got historical data including outdoor temp, RH, and ozone, and chemically resolved PM for OA and IA, where all OA was cast in the 2D volatility basis set framework. So phase state, this is basically like whether it's liquid or semi-solid or glassy from a particle, and this has strong implications on things like particle diffusion and equilibrium timescales. So the phase state can be estimated by comparing the glass transition temperature to the indoor air temperature, and then we did that over the 16 city set. And what we found was that most indoor OA was semi-solid rather than liquid or amorphous solid. And so this implies that maybe instead of using equilibrium partitioning assumptions in our modeling and in our mental framework, that potentially we should use kinetic partitioning frameworks instead. The next thing I want to highlight and question is whether nucleation or partitioning drives a lot of indoor SOA formation. We saw both in that model, or excuse me, that experiment before, and it's unclear when one regime dominates over the other. So we need to ask ourselves is whether a framework can be developed for delineating between these two mechanisms based on ozone VOC ratios and existing particle availability. A second to last research need is whether human squalene on our skin can react with ozone and form secondary organic aerosol particles. So in the interest of time, I won't talk about this too much, but we have seen this in our chamber work where we doused something, a petri dish with squalene, hit it with ozone, and then small particles were formed. And then my last research need, I'll just close by asking what are good mitigation strategies for indoor SOA formation? So I think we should be asking ourselves which terpenes are most important to remove from indoor formulations. This was hinted at with some of the modeling I discussed earlier. I think we want to ask ourselves how effective are standard particle filters at removing SOA, because this is a dynamic mixture. And after we remove some of the OA, will the system readjust, and how will that affect effective filtration efficiency? And then finally, what's the influence of ozone and OH producing technology, examples of BPI or UV, on indoor SOA formation? So this was one of the first things I did as a graduate student with Jeff Siegel and Rich Corsi, looking at ozone emitting ion generators in the presence of a terpene source. And so this was a consumer product meant to remove particles. And you can see that as it turned on and started generating ozone, it actually operated as a net particle producer rather than a mitigator. Okay, and so I'm just going to leave these future research needs here. I'm not going to re-say them all again in the interest of time, but these will be available if you want to look at them after the talk. And with that, thank you for your attention. I want to acknowledge my collaborators, and I'll take any questions you may have.
Great. Thank you very much for that excellent talk. So if there are any burning questions, we can ask now. I might actually have one I'm just curious about. I'll ask mine in the chair's prerogative. So Michael, your focus, you were talking about sort of, and this feeds beautifully from sort of the drivers of the VOCs that go to this SOA, which, and you look at the massive number of particles that are forming tiny particles, you have to wonder what those VOCs are. And so you focus largely on, terpenes and sort of those kinds of compounds, but are those the main ones? I mean, do we know anything about the other types? Because I mean, there's obviously lots of sorts of VOCs. So right. You focus there. So that's.
So the model did include other types. So the main part of the talk when I showed the residential SOA formation model, and I attributed it to different types of terpenes, and I called out alpha terpenine and limonene.
Right. Right.
Also on that plot were other classes of volatile organic compounds that were considered in the model, and their fractional amount of SOA generation was posed as well. And so, of course, if it's not an alkene, right, then it's only going to react with a radical like, OH or the nitrate radical. And so that was put into the model. It just was deemed as being less important to the overall SOA formation as the limonene and some of the other terpenes was. And just, I've seen this in sort of some previous other modeling I've done where it suggested to me that there can be often particular cases where 1 to 5 terpenes are so reactive that if they're present, they're just going to suck everything up, and they're going to drive a lot of at least the initial chemistry that's going on.
Okay. Yeah. I guess that makes sense. But my main question was like, do you feel comfortable knowing there aren't missing ones that could be driving things?
So I think there may be missing alkenes. And that was one of the points I was trying to make is, I was surprised with the modeling study where alpha terpenine, which had a very low concentration of like 0.0 something parts per billion, right, ended up being the second most dominant contributor in the model to the SOA formation. And it just made me realize that there could be a whole host of very low concentration, potentially high reactive alkenes or terpenes that may not really look that interesting if you measure them from like a total monoterpene perspective or something like that. But I think that we need to break it apart a little bit more thoughtfully and look at how reactive those are compared to sort of the bulk reactivity of all the terpenes. So I do imagine that there's a certain number of terpenes out there with, say, 2 double bonds, particularly. Limonene we know about, but like, alpha and beta and alpha terpenine, right, and terpenylene. These are examples of things that I think are sort of understudied indoors that are present in lots of products that I think may be at low concentrations because they're so reactive, but they still, because they're so reactive, may be contributing.
Yep, exactly. Yep. Okay. Well, thank you very much.
Thank you.
We'll move on. That was an excellent talk.